Okay, today is section 6.3, parametric equations and motion. I'm going to go through the first things pretty quickly because we've already been doing some parametric equations, but I'll give a quick review. This is example 1, and this is graphing a parametric equation. And I'm only going to do one of the intervals. You can look at the book. They're slightly different because of just the intervals. So x equals t squared minus 2, y equals 3t, and I'm going to do this interval. So again, I make my t, x, y table, and I'm going to just do integers here. T, negative 2 squared minus 2 is 2. Negative 1 squared is 1, minus 2 is negative 1. Negative 2, negative 1, 2, and 7. Y is 3t, negative 6, negative 3, 0, 3, 6, 9. So I'll plot x versus y. I'm going to start with negative 2, negative 6. I'm going to go to negative 1, negative 3. Negative 2, 0. This doesn't look like what points are showing on the negative 1, 3. Oh, I screwed up. This is positive 2, negative 6. That's why this doesn't look right. 2, 6 is here, and 7, 9 is here. And there we have it. That's the graph on the interval. Okay, I'm going to talk about eliminating a parameter. This is example 2. If you want to see the rest of the graphs, you can see them in the book. And remember, we must always give these t intervals. So eliminating the parameter, easiest way to do this is solve for t. I probably want it as a y equals equation, so I'm going to solve the x equals equation for t. Then I'm going to plug that in for y. I'll simplify this. And so I split up the 2 into 2 parts and made it 1/2 x. I guess the x should be behind it. It should not look like it's on the bottom. I do not want the x here. It's not with the bottom. It is behind like mx, which would mean it gets multiplied to the top. And that's how I would write that. So eliminating the parameter, key things is solve for t. A lot of times I want it in y equals form. So I will kind of solve like that. On this one, this is my first one. This one, they show you solving for y. If you solve for t in the x equation, you need the plus or minus on the square root. They're going to solve for y and say, now I'm going to plug it in and get, they're going to get what's a sideways parabola, a y squared equation. They did solve this for y. Again, I probably wouldn't with a y squared. That's a sideways parabola. That's example 3. Example 4, identifying a different graph. Okay, this one, cosine and sine. It's not supposed to go there. So we're going to look at our packet. This is in our packet. It's under equation forms. And anytime I have cosine, I have trig functions, I know it's going to be one of these conics. Because the two is the same, I'm looking at it and I see circle. So this is a circle. I have nothing plus or minus to change it, so it's plus minus. It's 2 is the radius, and it's circle centered at 0, 0. So that means radius is 2, so x squared plus y squared equals 4. Okay, in example 5, we are going to parameterize a line segment. And these are my endpoints. Okay, to do this, I'm going to run something in this form. The book kind of does it with vectors. I kind of often will do it like that. And the easiest two t-bounds are 0 and 1. So the first thing I'm going to do, I'll start at point A. It doesn't tell me, oh, this one says the parameterization of the line. So I'll show you a line segment and then I'll show you the line. Okay. So I'll show the line segment first, which is actually example 6. Same points, different t's, actually. So we're going to start at A at t0. So that means x is -2 equals A times 0 plus B. Guess what that means? B is -2. I know I'm going to get to point B then at 3, and that's going to be at time 1. And I can solve that A equals 5. So my x equation is 5t minus 2. we're gonna do the same thing here with y. We'll get CT plus D. You can pretty much tell probably that your B or D is your A point. And then I've got 6. Now I'm going to plug in 1 for point B. C is going to equal 3. So I'm actually doing 6 first, I guess. So I've got here 3t plus 3. If I want a line segment from those points, I'm going to run these t-bounds. This is example 6 with the line segment. I think the segment's easier. Actually, it's not really easier. But I do the process for the line the same. If I want a line that's going to continue forever, all I have to do is let my t continue going forever in both directions. So to make a line segment into a line, just don't limit the t's, let it go from negative infinity to infinity. Okay, simulating motion on a grapher. Okay, we're going to talk about using our grapher to note this motion along this line. Okay, so right now we have simulating motion on a line. And if we graph that just as it is, we can use parametric equations. And initially, we're going to set x equal to the equation that's given in S. I'm just going to write it as S. And y equals 5. Okay. Oops. Dude, that's what I want. Y equals 5. And that'll show, this is simply horizontal motion. That'll show the actual motion. So to do this, again, I go to mode, done this at one point, parametric. Now when I go to y equals, clear, I get negative 0.1 this is t to the third minus 20 t squared plus 110 t minus 85. And then we're going to go to y. So that's 5. Window here. T min. It says it's 0 to 12. Is my motion. T step. I'm going to go as 0.5. Just so this goes a little faster. X max. I think I need negative 10 to 10. That's got to be positive. This is negative 10. X scale 1. And now let's try graphing. That is not big enough. Okay. I see what it wants me to do in a different one. equals 8. Oh, I see what my problem is. I missed a decimal point. That would help. Okay, so now I can go to trace and I can watch the progress. The person initially starts here. They go this way. You can watch the cursor and then they go back. Now they're going backwards again. And we've reached 12. The motion's kind of a little funny. I'm going to set this as a second window. I'm going to type the exact same thing into Y2, except that's their actual motions. They're moving along a line horizontally. But it's hard to tell where they're going at each point because it's just going back and forth. So what I'm going to do is instead of setting Y at 5, we set Y at 5 so it wasn't on the x-axis last time. Now we're going to set Y as t, which this doesn't show the actual path they're going on. It just shows it relative to time. And I guess they did negative t in the book. The book did negative t to make it go down. So it's not overlapping the actual other graph. And now if I trace, you'll see it kind of goes the same thing, but then it starts hooking back like it was. And then you can kind of see if I go along my motion and go up, it's following kind of where the red is going back, and then switches direction again here, just like the red one does. Okay, simulating projectile motion. Okay, projectile motion is one of the biggest applications of parametric equations. Projectiles are anything launched or thrown through the air that has no propulsion as it goes. So a baseball, a bullet, all kinds of things are projectiles, and they are moving forward and falling through the air. Okay, a distress flare is shot up from a bridge 75 feet above the water with an initial velocity of 76 feet per second. V0, that's velocity at time 0, 76 feet per second. So as I'm doing a problem like this, I always want to get my things down that are given in the problem. And 75 feet is h0, or my initial height. It says, graph the flare's height against time and give the height of the flare above the water each time and simulate the motion. So there's a couple equations you need to know, and they are in your packet under equation forms. And there's a little section called motion, projectile motion. It's on the second page of that. And we are going to use the h of t with the 16 because that is, or in this case, y. H of t is y. That is for feet. Negative 4.9 is for meters if we're dealing in the metric system. And this is my basic equation. We then know that V0, I should say this is V0 in the y direction. So it's the velocity component, or the y component of the velocity vector. and this is the x component. So x, here's my parametric equations. So this particular one is launched straight up, which means V0x equals 1. So my particular parametric equations are and it says graph the flare's height against time and give the height at various times. So we're going to go to the grapher. I'm going to show you, not sure how much I've used the table. Well, this is going to be really easy to do with the table to get all these values. I'm just going to clear out these ones. Nope. I did that backwards. This is supposed to be t. Y is negative 16 t squared. That should have been plus 76. Yeah. And I'm sure I'm going to have to change my window. It's probably going to land in less than 12 seconds. Why min though? I'm going to make my maximum 1,000. I'm not sure how high it's going to go, but I would imagine it's kind of high. Okay, so not that high. Just need a couple hundred feet. This is generally its motion, and that's when it hits the water. If I want to get all these values, it wants me to get 1, 2, 4, and 5. I can set up a table. The table starts, so I want 1, so I'll just start at 0. And delta table tells me how often I'm going to have it. It's going to show me a value every 1. Second function of graph is going to give me this table. And I'm really interested in the height. So at 1 second, I got 135. At 2, 163. Or y equals 135 in this case. And this would work. This is straight up and down, so it's pretty simple. Okay. Um, so we can kind of just go 4 is 123, 5 is 55. We notice we've landed by 6. And that gives us our solutions. The flare's flight straight up and its fall to the water use parametric equations. So they kind of graphed it x equals 5.5 to see what the height is there. Our last one is going to be about hitting a baseball. Okay, so we're going to go back to the graph whiteboard, and we'll talk about hitting a baseball. So Kevin hits a baseball 3 feet above the ground with an initial speed of 150 feet per second at an angle of 18 degrees with the horizontal. So I got 150 feet per second here. And I got an angle of 18. So I'm going to break this into components. My x component being the cosine. And my y component, so I know cosine of 18 equals x over 150. or 150 cosine 18. So now my x component is 142.66. That means V0x is 142.66. My y component, I'll use sine. $46.35. So V0y equals 46.35. So again, here's my general y equation. Y equals negative 16 t squared plus V0 yt plus h0. The question is, will the ball clear a 20-foot wall 400 feet away? We know h0 also is 3, it tells me. And here's my general equation for x, V0 xt. So my specific equations here are this. And x equals 142.66 t. So it asks, will it clear a 20-foot wall 400 feet away? Well, if I want to know when it's at 400 feet, and I could graph this if I wanted and see. I can also just plug in and go x equals 400. And get a time. That's 2.8. And then I'm going to plug in 2.8 for t. And I get 7.17 feet. Okay. My height is 7.17 feet. Does that clear a 20-foot wall? No, the ball's only 7 feet in the air. It's bouncing off the wall. Unless the outfielder makes a great catch. Okay. That was example 9, and that is parametric equations.